All right, good morning. So today we are going to continue with one more effect that contributes to the non-ideality and the non-linearity of the BJT, right? So before we do that, let's go back to the beginning and take a look at how the transistor actually functions. So let me... All right. What is the primary reason we are able to use a BJT as an amplifier? Physical construction. 3 regions, 2 back-to-back PN junctions. But the reason it's not a symmetrical device is because of the doping profile and the physical geometry of the 3 regions. The most critical aspect of the construction is that the base region is very, very thin, right? If the base region is thin, then the charge carriers that come into the base do not recombine with the other charge carriers that are present in the base, whether it's N-type or P-type, right? So electrons combining with holes in an NPN transistor and holes combining with electrons in a PNP transistor. And most of the charge carriers that are coming from the emitter are able to cross over to the collector. So if the base region was wide, not thin, much thicker or wider, what would happen? More recombination. What? So that answer is correct. More recombination. So what happens to the actual current? It's diminished. It's less, right? So the wider the base, the less the device current. You all with me so far? What happens if the base width narrows? What happens to the current then? It increases, right? If it widens, then the current decreases. If it narrows, if the base region narrows or the width decreases, then the current of the device would increase, right? And that's where this early effect comes into the picture. That's an explanation for the early effect, okay? So just wanted to go over that so that you keep that in mind when we explain this phenomenon. All right, so early effect was named after, I want to say, James Early. He was a researcher who was working for, I want to say, either Radio Corporation of America or Bell Labs. Can't recall exactly which one at the moment. But what he noticed was that the collector currents, we say that they are almost flat, right? They are not dependent on VCE. That's what we stated previously. So we were ignoring all the other factors. We want a simplified model. We wanted a simplified explanation for a BJT. And so we ignored all the secondary effects. We ignored all the second order effects. Now we are introducing all the second order effects one by one. This is one of those. So instead of being completely flat, the collector current actually has a slope, okay? So it's not flat and it's not independent of VCE. Characteristic of a BJT would be that if VCE increases, collector current saturates, and not saturates, but it reaches a particular level for that operation, and then it remains flat. So collector current is not dependent on VCE. That's what we said so far. But in fact, there is actually a slope. And of course, this slope right now is exaggerated. So it's not as pronounced as what we see here, okay? And the reason for that is defined as the early effect, okay? What happens is if you take all these curves, if you take the transistor curves and you extrapolate them in the negative region or minus VCE, he found that all of these curves would intersect at one single point. So there is a slope to each one of these curves, and the slope is exaggerated. Okay, the slope is exaggerated. And if we extrapolated these curves to minus VCE, all of those curves would intersect at one single point. That point is known as the early voltage. Named after its discoverer. Okay. So the current actually increases, it does not decrease. Okay, so VCE, if you go in excess of 20, 25, 30, 40, 50 volts, would increase. The increase would be a minimal amount, but it would increase. It would not be flat. So there would be a slope that is present. And if you extrapolate that in the negative VCE region, it would intersect. All slopes, or I mean, all lines would intersect at one single point. The value of that point would be minus VCE. That is known as the early voltage. Okay. And the reason for that phenomenon is this. If this is the transistor, you would forward bias our base emitter region. Base emitter region, the depletion region will hold constant at 0.6 or 0.7 volts, which is right here. Let's just say 0.7 volts, right? Emitter base junction. But the collector base junction is reverse bias. If you reverse bias a PN junction, what happens to the depletion region? It expands. If it's expanding, where can it go? It cannot go anywhere else except into the collector and base semiconductor material. And because the depletion region is expanding, the effective width of the base is decreasing. And because the effective base width is decreasing, the collector current is, or the device current is, increasing. Yes. Yeah, the early voltage is negative. Yes. No, I mean, no, this is for forward active mode, because base emitter junction is forward bias and collector base junction is reverse bias. If you were to flip it and both junctions are reverse bias, yeah, that's what it's. I mean, all right, you confused me. Me too. But think over this, okay? So depletion region for the collector base is reverse. I mean, sorry, collector base junction is reverse bias. So the depletion region at the CB junction is increasing. Because the depletion region is increasing, the base width, the effective base width is decreasing, and hence the device current is increasing. Yes. In these plots, what are we ignoring? The one that goes flat. Oh, you mean like the transistor curves, like these? These? So even in here, as I showed, that has a slight slope. Again, even in this image, it is exaggerated. And you will see when you perform, if you have a lab setup, instead of being completely flat, you might see some small increase in voltage. But if you zoom out enough on the numbers or in the graph, it might appear as if it's completely flat. Right? The change might be, depending on what kind of transistor we have, depending on what kind of biasing we have, the change could be very, very small in millivolts. So if your scale is in volts and the change is only in millivolts, it would appear as if it's completely flat. Yes. question being asked is if you take these lines and extrapolate it to the left, would we reach the earlier voltage? That's absolutely correct. Yes, that's how we discovered this phenomenon. And again, since the slope is very minimal, the early voltage typically is in hundreds of volts. Right. So here we show about 15 volts, but typically it would be around hundreds of volts. Okay, hundreds of volts. But again, the phenomenon that explains this is this: base width decreases. Okay, base width decreases. All right. Let's see. Determining the operating mode. All right. Determining the operating mode. We have 4 modes of operation, right? Forward, reverse, cutoff, and saturation. So whether it's a PNP transistor or an NPN transistor, these modes of operation remain the same. Okay. Here in this example, we are using an NPN transistor, but it applies the same for PNP, except the polarities would be reversed. Polarities would be flipped. So if you have the voltages where the base is connected to negative and the collector and emitter junctions are both higher than the base, right? So VCB is positive and VEB is positive. Actually, should be the other way around. B, C, and E. Collector and emitter are both higher than the base. So VBC and VBE are both negative. Okay. So what happens then? Cut off. Then you have the base, collector, emitter, and both junctions, VBC and VBE, are positive. So base is higher than collector and the emitter. NPN transistor, both junctions are forward bias. So this would be, only one person knows. I think everybody does at this point. Okay. So again, if the base voltage is lower than both the collector and emitter voltage, then the transistor is in cutoff. If the base voltage is higher than both the collector and emitter voltages, then the transistor is in saturation. And then, of course, we have the active mode where the base emitter junction is forward bias and the base collector junction is reverse bias. And this is the active mode. So one kind of analysis we can perform is to determine the voltages at each of these terminals and then look at this diagram, or basically determine which voltage is higher than the other one, meaning VBC and VBE. Okay, VBC and VBE. If VBC and VBE are both positive, transistor is in saturation. If they are both negative, then the transistor is in cutoff. And if one of them is positive, if VBE is positive and VBC is negative, then it's an active mode. When we bias our transistor, we apply a DC voltage to our transistor, right? So if you wish to use it as an amplifier, which is something you'll be designing for Lab 8, right? For Lab 8, you're going to design a BJT CE amplifier. So you want to bias the transistor in the active region, meaning you're going to apply a DC voltage at the base and the collector so that the base emitter junction is forward bias and the collector base junction is reverse bias. So biasing is applying DC voltages. So it's somewhere in the middle of the active region. and then you apply your AC signal on top of that DC voltage. And the variation in the AC signal is going to move your transistor either to cutoff or to saturation. Just reverse active. Yeah, completely off. Question being asked is if base emitter junction is reverse bias. That's actually the first we'll see on the next slide. The first step in analyzing for the operating mode is to look at the base emitter junction. Everything starts from the emitter. Okay. If the emitter base junction is not forward bias, the charge carriers aren't going anywhere. So VBE must be positive. If VBE is negative, then the rest of it doesn't matter. Reverse active mode, yeah, saturation current. So we would obtain curves, but again, it would be like a reverse bias PN junction. We tried to measure it in the lab, if you remember, from the diode reverse bias characteristic, and you won't see any current flowing through. Yes, that is also one experiment you would do. So those of you who are in my lab class, in the lab notebook, the first procedure we do is sweep and go. We determine the terminals of the collector. So the question being asked is, base emitter junction behaves like a Zener diode. And because it behaves like a Zener diode, you would reverse bias both junctions using sweep and go in the lab. And whichever junction breaks down with less than 10 volts, that would be the base emitter junction. The middle terminal is always the emitter. Middle terminal is always the base. And so you would connect a second lead to the outer terminal. If it breaks down within 10 volts, that's the emitter. If it doesn't break down within 10 volts, that's the collector. So that's a quick and easy way to determine the pin configuration of any BJT. Okay. All right, let's look at an example. Oh, any questions before we look at the example? Okay. All right, so I'll give you a couple of minutes, go through this, and you should be able to tell me what the operating mode is. All the voltages are given to you, so determine VBE and then determine VBC, and then tell me what results you obtain. And then I will go over the solution. Okay, so VBE, what do you have for VBE? 0.7 volts, because VBE, VB minus EE. So what does 0.7 volts tell us? Right? PN junction, base emitter junction would be in forward bias. Then VBC, VB minus VC. If you obtain a positive voltage for this, that means that this junction is also forward bias. So that means it would be in saturation. But the conclusion from a forward bias base emitter junction means that it is not in cutoff. Okay, so we have eliminated the first possibility. If this value was negative, if VB is negative, we do not proceed further. We can directly conclude the transistor is off. Okay. So regardless of what happened to the other junction, if the base emitter junction itself is reverse bias, nothing's going to happen. Okay, so that's one key point to keep in mind. Anytime you're troubleshooting circuits or trying to determine the mode of operation, and again, this will be particularly relevant when you get to 307 and 308, right? So if you're looking at circuits, if the base emitter junction is off, nothing else will happen in the transistor. The transistor BJT would be off. So that's the first thing we always check. Base emitter junction, forward bias, and it's either in active or in saturation. So let's look at VB minus VC. What do you have? Minus 2 volts, negative. That means junction is reverse bias and transistor is in active mode. Okay, transistor is in active mode. For saturation, we can run one more check. Okay. We can either check the base collector junction, or we can look at the voltage VCE, collector to emitter voltage. If the collector to emitter voltage is 0.2 volts, 0.2 volts, then the transistor is in saturation. VCE, remember from the characteristic curve to the left side of the graph, starts sort of linear and then quickly saturates. Cutoff is right at the bottom. Saturation is to the left, very close to the origin. So VCE is 0.2 volts or less, then transistor is in saturation. BJT is in saturation. So here, if you want to check, you can do VCE is VC minus VE, and we obtain minus 1.3, we get 2.7 volts. Therefore, not in saturation. That only leaves active mode. Okay, that only leaves active mode. There might, yes. If VBC was 0, meaning no voltage applied or the same voltage applied, it's a good question. Would be off. The question being asked is, what if VBC was 0? And you can try that out in the lab today if you wish. There's also one more case if VCE is 0.4 volts or less. Okay. If it's 0.4 volts, 0.3 volts, there is a state where we say it's on the edge of saturation. So it's very close to saturation. It's not yet saturated. Say it's on the edge of saturation. So it's either in saturation or in active. Then we do a few more calculations. Yes. Uh-huh. For BJT, yes, to the left, close to the origin. Yeah, yeah. In the FETs, in the MOSFETs, it was the triode region or the linear region. And cutoff in a BJT is close to the x-axis where Y value is 0, no more current. But cutoff in a FET is different. Yes, yes. This question being asked is, does there have to be a value for the VBC voltage? Not necessarily, no. As long as the junction is off a reverse bias, that would mean it's, in active mode. Negative 0.1 volt would still mean it's reverse bias and it's active mode, yes. Okay. So this was a straightforward example where the voltages for the terminals are given, right? So this is just, it's a prep, it's the first step. Now let's look at an example where we need to determine the operating mode, which would be the case for any BJT circuit or a transistor circuit, but the voltages are not given, so we have to determine the voltages, right? You have to determine the voltages. Beta value is given, it's 125. Determine all BJT voltages and currents. That means all would mean all terminal voltages and all terminal characteristics. Fortunately, we have equations that relate all three quantities to each other, right? We have beta, so we can find alpha, and then we can find IC, IE, IB using those relationships. All right, what do we notice first? Dual power supplies. Collector is positive, emitter is connected to negative, plus minus 5 volts. And the base is connected to ground, a reference point of the power supply. So what is the value of VB? 0 volts, right? So we see VB is 0 volts. By the way, we can also draw this circuit diagram. And sometimes it helps me to visualize things a much better, easier way. For instance, if I'm applying KVL, which we need to do to find the voltages, this kind of diagram helps me visualize things. And so this would be 5 volts, and this would be 5 volts. And because we're connecting the negative end of the first supply to the positive end of the second one, we are shifting the level for the second one below reference point or below ground, hence minus 5. Okay. Typically, you will see problems that simply show you the terminal voltages, do not show the entire power supply. As a student, I always found it hard to actually apply KVL, or visualize things just as it is. So I would redraw the circuit with the power supply itself. All right, so if we wish to find the voltages, what can we use? KVL, right? KVL comes to mind. So I would apply KVL in the loops. I can apply it on the input side, on the output side, and see what voltages I get. Let's make an assumption, since we are trying to determine the operating mode and we don't have the voltages, let's make an assumption that the base emitter junction is forward bias. right? We can assume it to be off if we wish, but it makes rather sense that it might be forward bias. If it's forward bias, then what is the value of the emitter? -0.7, yes, but -0.7, yes. Because base is at 0. So if base is higher than the emitter by 0.7 volts, that means emitter is lower. So with respect to our reference point, it would be 0.7 volts less. So -0.7, right? We're beginning our analysis based on this assumption. So if we have the emitter voltage, meaning at this point, at this node right there, then I can find the current IE. IE would simply be -0.7 minus of -5 divided by RE is 4,300. So this gives me 0.001 amps or 1 milliamps. Now we can find IC. Since we have IE, we can find IC, we can find IB directly from there. If we wish to find IC from IE, we need alpha. Yes. Superposition, yes, you could. But it's superposition simply means we analyze with one source active at a time. So if I'm applying KVL or Ohm's law either to the top loop or the bottom loop, I'm only looking at one voltage source anyway. So in a way, we are applying superposition in that sense. We are only looking at, so if I apply KVL here, or if I apply KVL here, no, but if I'm applying KVL, I just need one loop, one electrical loop. And the other voltage, if I apply KVL to the top loop, I do not have the second power supply in the top loop. If I apply KVL in the bottom loop, I don't have the other power supply in the bottom. It would be a simple straightforward application of KVL. VBC and VBE would be in there, but not the other voltage supplies. All right, so IE is 1 milliamp. So let's find alpha from beta. Alpha F is beta F over 1 plus beta F. You plug in the values of beta F. Comes out to be 0.99206. 0.99206. So what is IC? Anyone? IC and IE would be very close in value, right? 99%, 99.21% of IE. So, let's see, 192. I got 0.992 milliamps. So this is IE is 1 milliamp. It's a straight up multiplication. You get 99.2 microamps or 0.99206 milliamp. 1 milliamp. And now we can find VC. Yes. Yes, because we were given beta. I can write IC, the collector current, as the current that's flowing through the resistor RC. And so that would come out to be I minus VC over RC. What is VC? Anyone else? I have about 3 volts, which 3.01, yeah. Okay. So then what is VBC? -3. And if VBC is negative, then the transistor is in saturation. No one's listening. I just said saturation. What mode is it in? It's an active mode. Just checking to see how many were listening. All right. Let's take a pause. Let me know if you have any questions. Yes. In a PNP transistor, is alpha F equal to? Oh, if these equations are valid for PNP transistors? Yes. All the fundamental equations that we looked at are equally valid for PNP transistors. The only thing is holes are swapped with electrons are swapped with holes. So the current direction is completely flipped and the voltage polarities are also flipped. So instead of VBE, it would be VEB. In a PNP transistor, it would be VEB because the emitter would be N type, the base would be P type. Sorry, PNP transistor. So emitter is P type and the base is N type. So the emitter should have a higher voltage in the base in order for it to be forward biased. So VBE would be negative, VEB would be positive in a PNP transistor. Hence, voltage polarities are flipped. If VBE is positive in NPN, in a PNP, it is negative. Yes. Mm-hmm. Yes. So question being asked is, based on our assumption, we obtain a negative voltage, so we can conclude it's active. But if it appeared to be a positive voltage, then the answer is our assumption would be incorrect. We'd go back and make a different assumption. Yes. Uh, okay. Yeah, no, that's a good point. Yes. So that would just mean it's in saturation. Then we'd look at VCE also. That would be the third check. So if VBC is positive and not negative, then it could be in saturation. If it's in saturation, then VCE must be 0.2 or 0.3 volts. That would be the third check. But if VCE does not come out to that value, then we'd go and change our assumption at the top. Okay. Yes. Yes. That is a material property of the transistor. The beta wouldn't change just based on the voltages. Whether it's in saturation or not, beta F is a property of the construction and the doping profile. That would not change. At least not within the constraint of this problem. It does not change. No, it still applies. It would still apply. For fundamental equations, we can still use that beta F. Okay, let's look at different biasing circuits before we end class for today. All right, so we're talking about biasing, right? DC bias. So there are different ways to supply power or DC voltages to the base, to the input side and the output side. Okay. So far, we looked at circuits where we have to apply a positive and a negative voltage, right? Positive voltage to the collector, negative to the emitter. The downside, of course, is we need two power supplies to accomplish that, right? Here is a straightforward circuit. We simply connect a resistor to the base, resistor to the collector, and you apply the single power supply to both terminals. Okay, that establishes the base voltage, and it also establishes the base current IB. Okay, so we take a power supply, connect it via a resistor to the collector and to the base. So depending on the value of RB, depending on the value of RC, we can establish a base current, a base voltage and a base current. Okay, and then we apply AC input and this terminal on top of our DC bias. Same thing is accomplished in the second circuit. The second circuit, we have a emitter resistor. So the emitter is also at a fixed voltage. Hence, it is known as an emitter bias circuit. Okay, so the first one is fixed bias, where the voltages VB and VC are fixed. Our VE is fixed. In the next one, we have a emitter bias, where we bias the transistor via the emitter voltage VE. Now, the downsides of these two is that the output Q point, VC and IC, are dependent on beta. So the downside is the Q point is dependent on the value of beta, which fluctuates even if the same transistor is made at the same time. So beta values vary from transistor to transistor. Okay, even if you create two transistors on the same chip at the same time using the same fabrication process, the beta values are different. For the simple reason that we're talking about millions and billions of atoms, actually much, not even billions. We're talking about like 10 raised to 18, 10 raised to 19, 10 raised to 20 dosage, right? Atoms per centimeter cube. So with that, huge volume or huge number of atoms that are used for doping, it is impossible to control a doping profile down to the single atom, right? And so beta values will vary wildly between the same transistors. So we do not obviously want to have that. We want to design circuits where if you create a circuit, let's say on a breadboard, you create your C amplifier and you blow out your BJT, it doesn't work. Then you plug a different one in there, but your circuit now doesn't work because the biasing doesn't work, right? And so there is something that we use known as the 4-resistor bias, where you have 4 resistors connected to the BJT. There's one at the collector, one at the emitter, and there are 2 at the base. The 2 at the base that are noted as R1 and R2, also sometimes noted as RB1 and RB2. If you look at them in isolation, they create a voltage divider network, 2 resistors in series, if you just look at them in isolation. So the middle point of that voltage divider network goes into the base terminal. Okay, so the value of R1 and R2 will decide what is the base voltage. Since it forms a voltage divider network, it is also known as voltage divider bias. It is by far the most popular biasing scheme, and it is independent of beta. Next class, we'll look at equations and some derivations where we can derive the expression for the output, and we will see that beta is absent in those equations, right? So we'll end class here today. We'll pick up here on Friday, where we will design a BJT CE amplifier for next week. Those of you who are in my lab class, I'm going to open up the lab early. So those of you who wish to come in early and get started, I will have it open around 2:15. Okay, I will send an email to everyone just now. I'll go ahead and send it out. Yes, but it can be, if you work correctly and efficiently from the top, then we can get done within 2 hours or 2.5 hours easily. Why not? I have confidence in you, in all my students. Well, that's what I'm here for, to build up your confidence. So we'll see you all in the lab.